Hi everyone, my name is Vibha, and today I'll be presenting my research on using machine learning to predict exoplanetary system characteristics from stellar light curves. So, first, a little about me. I'm a junior at Monte Vista High School in Cupertino, California, and I've been fascinated by astronomy for several years. I've competed in Science Olympiad astronomy events, participated in the US Astronomy Olympiad, and I'm also the upcoming president of my school's astronomy club. Apart from astronomy, I'm also really interested in computer science and machine learning. So that's what inspired this project, and it's a combination of the two topics. So let's talk about why exoplanet detection is important. So it's one of the most exciting areas of astrophysics today, and it's important for several reasons. First, it tells us how common planets are and whether like solar systems and planets in our solar system are common or not. It also shows the diversity of planetary systems since we've already found planets unlike anything in our solar system and also planets that resemble planets in our solar system. It also informs habitability studies by identifying planets in the so-called habitable zone where conditions might allow life. So this is where liquid water exists. And it also pushes forward astronomy and computational methods. We now know of over 5,000 exoplanets, but we need to find a way to characterize them, such as knowing a planet's radius, orbital period, and how many planets are in a system, and this can help us understand how planetary systems form and evolve. And ultimately, this research gets us closer to answering a big question, which is whether life exists outside of the Earth. So one of the main ways we detect exoplanets is the transit method. When a planet passes in front of its star, we can see a small dip in brightness in the star's light curve. And by analyzing these dips, we can infer properties of this planet. So as you can see on the diagram on the right, we can have a graph of brightness of the star versus time. So when a planet passes in front of a star, it blocks some of the light that the star emits, and so we can see a dip in the brightness. But this method comes with challenges such as noise from the telescope and the star, which can obscure the signal, and also multiple planets overlapping. And this makes the dips from each planet harder to separate. So translating from dips in brightness to actual planetary parameters like the orbital period and its inclination is a complex nonlinear process, and this is where machine learning can help. Unlike traditional approaches, machine learning can learn patterns directly from large amounts of data and adapt to complex overlapping signals in ways that are difficult to hand code. So my research question is, how can a machine learning model be trained to accurately predict the characteristics of a planetary system from a host star's light curve? So this is what my research is going to be trying to address. So first, let's go over some important terms in order to understand the structure of my project. So let's start with deep learning and convolutional neural networks. So a neural network is a kind of network that's inspired by the brain, and you can think of it as layers of connected neurons, and each of these neurons holds a piece of information, and each layer transforms the data. So over here, the arrows on the upper diagram represent the layer, and this layer transforms the data to create different parameters, which is, so it transforms from the purple to the yellow. And it transforms this data through mathematical functions to change it in some way. And this is done to make patterns within the data easier to see. So for example, in my project, a layer might combine flux values from nearby points in the light curve so that a small dip caused by a planet stands out more clearly against the surrounding noise. And flux is just another term for the brightness of the star. And so deep learning just means that we use many of these layers that transform the data. And so each layer does its own transformation, and stacking them lets the network capture complex relationships in the data. A convolutional neural network, or CNN, is a special type of neural network which instead of looking at all the data at once, it uses filters that transform the data to highlight local patterns. So, for example, in images, that could mean edges or shapes in the image, and in light curves, it means dips, slopes, and periodicity. And so CNNs are a good fit for this project because they can transform the light curve data so that even small dips from planetary transits can stand out, even if the light curve is noisy. Additionally, I've used generative adversarial networks, or GANs, to create synthetic light curves in order to have data to train my model. So GANs have two parts, a generator that creates data and a discriminator that tries to tell real data from fake data. So they train against each other until the generator produces realistic outputs. So for example, in this diagram, um, you're given real images to the discriminator. The generator tries to mimic those real images, create fake images, and then the discriminator looks at those generated images and tries to tell if they're real or fake. So the generator's goal is to fool the discriminator into thinking that its generated data is real. And the discriminator's goal is to tell if an image is real or fake. So together, if they work against each other, they can make the generation of the data better. However, one common issue for GANs is mode collapse, and this is when the generator only learns to produce a narrow range of outputs instead of the full diversity of possible light curves. So to address this, I used a Wasserstein GAN with gradient penalty, or a WGAN GP. This is a subset of a GAN, and this is designed to improve training stability and avoid mode collapse. So in my project, I used WGANs to generate and refine synthetic light curves so that they resemble real telescope data more closely. The reason for this is that there's limited telescope data that I have. So if I have a way to generate an unlimited amount of realistic telescope data, I can use it to train my model and make it better and better. So these synthetic light curves will then be used to train my model so that it can accurately predict exoplanet characteristics. So another important piece of my project is the Mandel-Eagle model. So this is a physics-based model that generates the exact shape of a transit light curve given planetary parameters, things like orbital period, planetary radius, and semi-major axis. So in my pipeline, I use Mandel-Eagle as the reference point. My machine learning model predicts planetary parameters, which I then feed into Mandel-Eagle to reconstruct a light curve. The loss is calculated by comparing that reconstructed light curve to the original data, which ensures that the predictions remain physically realistic. So I'm given an input light curve, and my model is going to try to predict the parameters of that light curve. So once it has those predictions, those parameters are going to be fed into Mandel-Eagle, which is going to create another potential light curve. So this potential light curve is going to be compared to the original light curve, and loss is going to be calculated based on how different they are. And that loss is going to be used to refine my predictions. So here's an overview of my entire machine learning pipeline. So first, I generate synthetic planetary light curves using a WGAN GP, where the generator learns to mimic Kepler-like data and the discriminator enforces realism. Second, I inject realistic noise with Gaussian processes to capture variability in stellar and instrumental effects. So once I have my synthetic light curve that's generated by the WGAN, it still doesn't resemble a real light curve because in a real light curve, there's going to be a lot of noise from external factors. So I inject that noise with Gaussian processes. I then refine the synthetic light curves by comparing with real Kepler data. After that, I trained a CNN model to predict transit parameters like radius ratio, period, and inclination from my light curves. I then used those predicted parameters to reconstruct light curves using the Mandel-Eagle model based on predicted parameters. After that, I evaluate performance by comparing reconstructed curves against synthetic and real Kepler data. So now for my results. Um, After extensive training, I've unfortunately only been able to confirm my results for inclination so far, where the error rate is 4.2%. Basically, that means that my predicted answer is within 4.2% of the real answer. But I will be able to gather more results after further training of my model. So to summarize, this project combines physics-based modeling and machine learning to improve exoplanet characterization. It uses a GAN to generate synthetic light curves to train the model, and then uses another model which discerns the characteristics of the exoplanet, using the Mandel-Eagle model to calculate loss. And in the future, I hope to apply this to multi-planet light curves. Thank you.
Vibha, thank you so much for that great presentation and the exciting work you shared. So any questions from the audience or the other panelists? Okay, while others think about their questions, let me ask one. So Vibha, this is very exciting. Exoplanets are obviously an active area of research. Do researchers in general use machine learning to detect them? Is that the main method?
I think that there has been an increase in the use of machine learning. I think like prior to this, like around 10 years ago, people were predominantly using like like methods like Monte Carlo, Markov chain Monte Carlo, like Vincent mentioned in his previous presentation. But I think that there has been a rise in using machine learning to improve efficiency and to improve how fast um, you can predict these parameters.
Got it. I see. And you mentioned that you generated synthetic data. Is there actually real data available to researchers like yourself?
Yeah, so it's on a website. It's Kepler release data. I've been using the confirmed exoplanet release data. There's around like 35,000 light curves on there. So that's like a good reference point to generate more synthetic light curves.
And so in your pipeline, you did use real data to enrich the synthetic data. But
Yes, I did. So I used it to actually like I used it to model my synthetic data off of so that it would like maintain its realism.
and maybe you said this, but I'm just curious. So why, what motivated you to use synthetic data when there is also real data available?
It's because while 35,000 might seem like a big number, it's actually not quite enough data to train the model. So I needed a way to generate like an unlimited, like how much ever I want, and an unlimited amount of data. So that's why I created the synthetic data.
Got it. I have more questions, but any questions from the audience or panelists? How many? So you mentioned you need a lot of synthetic data. Can you give us a ballpark? How many curves you generated?
Um, how many curves? I think like a little more than 100,000.
Oh, wow,
Yeah.
that's impressive. That's a lot of data. Yeah.
Yeah.
Okay, so we have a little under 1 minute left. What was the most challenging part of this project for you?
It was definitely dealing it was definitely writing the code because first I had to write my GAN, and I think I struggled a lot with the mode collapse issue that I was talking about because it's it's like it's really easy to fall into like a local minimum where it can fool the discriminator easily, but that doesn't actually capture the whole diversity of light curves. And for my other model, it was definitely like being able to predict all the parameters because if there's not a lot of information in the light curve that's provided, so the model needs to work really hard to infer all the parameters realistically.
Got it. Well, Vibha, thank you so much. Very exciting, and we look forward to the future results that you previewed.
Thank you.